I'm Hojjat. I'm a graduate student at Caltech, and my work is on induced seismicity forecasting with uncertainty quantification, with application to Groningen gas field. And this work is a collaboration with Seismo Lab. A lot of people have worked on this project and helped me through this work. So let's have a little bit of background about this project. So in the right panel, you can see the Groningen, which is a state in the Netherlands. People have started extracting oil from this area in 1970s, and after 20 years, people start to feel some earthquakes happening in that area. To model and describe this behavior, we use the recent paper by Hamischen 2022 that finds a functionality between the stress distribution in time and space to the seismicity rate. So basically, given the stress distribution and having some other parameters, we can find the total number of events. So in this project, we, given the seismic catalog that we have and the oil extraction using vertical flow models, and this is a specific paper by Smith et al. 2022, we find the stress distribution in that area, and then we invert for these four parameters to find the seismicity rate and also to quantify its uncertainty. So in this project, we answer different questions. For the sake of time, I have selected these two to introduce to you. So how can we quantify the uncertainty in the model? What is the best likelihood function that we can use? And what if we had a better seismic network, or are the model parameters constant in time? And what is the maximum moment estimate given all the data and information that we have? So for the uncertainty quantification, we have to add two main sources of uncertainty. First, we don't know the exact model parameters in the equation that I just showed you. Also, the model that we have predict the rate of events, and it doesn't necessarily give you the exact number of events. So given the rate of an event, you don't know the exact number of events, and it follows a Poisson distribution. So to quantify the uncertainty, we have to pile up all these sources of uncertainty. So this is a sample output of our work. So here, the white area is used as the training set, and the dark area as the test set. The yellow line here is the catalog, and after inverting for the parameters, we could find this MLE, the Sion line here, and these red lines are the predicted the rate that we have predicted in 98% confidence interval. We also could put bounds on the total number of events by adding all the sources of uncertainty. Another interesting question that we are really interested to answer is that what is the maximum moment estimate? So to do this, some people use Gutenberg-Richter distribution, but here we have a challenge that because we want to do a forecast for the future, for example, up to 2030, we don't know the total number of events. We also don't know the exact value of the B value. So we have to use a strategy. So so given our a maximum likelihood estimate, we can find a total rate of the events. And given the rate of the events, we can randomly sample from that to get the number of events. And then we can also sample from the B value distribution. So here you can see we have the B value, and we can construct a distribution for it, and we can sample from it. Also, given the oil extraction scenario for future, we can find the rate of events, and then from that rate, we can IID sample from the rate of events to get one realization of the number of events. And then by adding these two variables here and here, we can sample from the Gutenberg-Richter distribution. So here's the result of our work. So you can see different realizations considering all these three sources of stochasticity. The blue line is the expected value of the Gutenberg-Richter, and the red one is the observed number of events greater than a magnitude, greater than a certain magnitude. up to 2021. And in the bottom plot, you can see the distribution of the max that we have found. So the value that we have found is up to 2030, and the observed one is up to 2021. In the last plot here, you can see the evolution of probability of exceeding certain magnitudes. So for example, here you can see the magnitude, the blue line is the magnitude 3.5, and you can see the expected value for exceeding certain magnitude is monotonally increasing in time. And for example, in 2013, we are almost sure that we will pass magnitude 3.5. That was my talk, and the main takeaway is that with this approach, we can forecast the number of events, we can quantify its uncertainty, and we also can have some sort of estimate on the expected maximum magnitude. Thank you for your attention. This is my email and my Twitter. If you have any question, please contact me, and I'm also here. If you have any question, I'm glad to answer.